All right, good afternoon, everyone. Welcome to this special BINR seminar. And it's really my great pleasure to introduce our guest speaker today, Professor Vasant Kumar, who is the head of the Materials Chemistry Group at the University of Cambridge, and most importantly, a graduate of McMaster University. Professor Kumar did his PhD in the Department of Metallurgy at the time, right?
It was metallurgical engineering, I think.
Under the supervision of Professor Alan Key. And then he went on to join the University of Cambridge. And along his journey, he published more than 360 journal articles. He has 20 patents, and I guess 40 PhD students or more were fortunate enough to work with him, as well as about 40 postdocs as well. And we're so happy to welcome him back and to listen to some of the work that he has done on a wide range of topics related to energy. So the one he picked for us this afternoon is related to batteries, but later on, people are welcome to stay on and talk a little bit about metallurgy and greening the steel industry as well. So that's another area that he's very interested in. So thank you so much for making time.
Thank you. Thank you very much, Professor Hatem Zurab. Yeah, thanks a lot. It's great to be back here. It's great to be back here in decades. Yeah, but of course I visited along the way, and it's nice to see some of my friends from a long time ago. It's Money here and John Weaver, and few others is Katie Jacob. I know all of you from before in my life in Canada, and nice to meet some great new friends. And of course, I met Hatem today, and thank you very much for your hospitality. And it's been great to be back. And I can see that the whole tradition of hospitality and friendship continues here. I mean, that's what I remember as a memory of McMaster University, is that the great friendly university, and that all students and all staff, everybody thrives here. And so glad to be back here to be part of this this actually tradition that I take with me. And I used to always tell people when I go to Canada, it was fantastic. When I go to Cambridge, we had this fantastic way of collaborating with each other and great scientific discussions. And I hear from Hatem that continues. This is a great tradition. And every professor in the department, I knew them really, really well. And across the university, I have made so many friends. I played a lot of basketball. John Weaver is kindly here. We played so much basketball here, every day. Yeah, that's right. And without that, I could not have done my PhD. Probably I would have done it a bit faster, but it would have been less enjoyable. Thank you very much. I think, as we all know, that the energy and environment are so significant in our discussions at the moment. And it is also correct to say the lithium-ion batteries is going to be a dominant technology in the area of energy for time to come. And however, as university researchers and academics, we should also pay attention to what might follow, what else is in the horizon that we want to work on. There's a whole range of chemistries, energy, materials, chemistry that are important. And I picked lithium-sulfur as perhaps the front runner. Yeah, okay, could be proved wrong in that, but there are competing possibilities, like sodium-ion is another one, and sodium-sulfur in new variants. Sodium-sulfur has been around for a long time, but new variations are coming in the horizon, but even aluminum and magnesium and zinc. Yeah, and of all these elements, and when I mentioned, Canada is actually rich in all these elements. And take lithium-ion battery alone, the supply chain that's available in Canada, the resources available, is going to be key. Everybody's paying attention to Canada. And of course, I don't know what exactly is happening here, but we know that Europe does not have the resources, but has huge ambition. Yeah. So, and therefore, I can imagine that Canada will have a big part to play, whether it's nickel or copper or cobalt or scandium or chromium. All of these become very, very critical and of course, iron and steel is the mainstay of Hamilton. And that's, in a way, that's what brought me here to understand. If you understand iron and steel material science, from phase transformation and to manufacturing and recycling, you know a lot of material science. I think it covers all those fundamentals relevant to every other field that I go back to my basics that I learned here in McMaster University. Okay, so I think let me just give you some flavor of where we are heading in this area. If you look at the lithium-ion battery, yeah, so the simple cartoon here is that there are two crystal structures. One is the very basic carbon, the graphite, with its yeah, see, I see what you mean. Yeah, great, thank you. Yeah, so this structure that is shown on the right-hand side, it is able to intercalate lithium into the structure. Yeah, on the left-hand side it's an oxide, could be lithium cobalt oxide, being the most common one at the moment for all the batteries that we use in our laptop and mobile phone, and the other chemistries that are following, especially for the electrical vehicle applications. And these are also layered structure. As a result of that, they intercalate lithium into the structure and deintercalate. Yeah. So therefore, when a battery starts its life, the lithium is in the wrong place, it's in the oxide. And then by charging it, it is a formation stage, you put the lithium into the carbon. And as a result of that, the battery has the energy and the potential of 4.2 and has a certain energy capacity. Now, if you look at these figures here, the graphite anode carbon structure, graphite has an energy capacity. If you look, it's a capacity in terms of charge. It has 372 milliamp hour per gram. And if you look at the cathode, the value is somewhere between 100 to 200 milliamp hour per gram. Yeah. Okay. Thank you. Thanks a lot. Yeah. Yeah. And overall, the combination of these materials, we have to grammatically calculate, depending on the amount of material, how much capacity you could have in these batteries. Yeah. It's pretty good, it's the best, but it may not be good enough for the future. So we have to start thinking about how much more demand that the consumers will make, yeah, to make a really, really long-staying technology. Yeah, because otherwise that'll be limiting. But if instead of graphite, one way to use lithium is capacity is 3,860. I mean, that's the beauty of lithium. It's got so much energy, but by putting this structure for basically mainly for safety, we go down to 372. Yeah, 10% less than 10% of the capacity. And sulfur, I picked sulfur here as a potential element. It's non-toxic, does not have cobalt and nickel things or any heavy metals. And that has a capacity of 1670. Look at that. Therefore, this is a prize worth fighting for. It's very difficult. If it was that easy, you would have done it by now. This idea has been suggested ages ago, yeah, but never been able to be successfully followed. But this is why, for a researcher, this is a great challenge. Yeah, and we have so much now developments in microscopy and various spectroscopy techniques that we are able to now understand why this is difficult and how we can solve the problem. I think, yeah, periodic table is key, but I'm not going to spend too much time on this one. I mean, a lot of anodic materials exist, for example, the lithium, sodium, magnesium, potassium. Also on this side, traditionally silver batteries, there are zinc, copper, and aluminum, and also lead. These are the traditional elements with energy density in them, and therefore they need a host, which is the cathodic material, where it maybe makes made of oxides and sulfides, or sometimes they can be pure. For example, we saw carbon, oxygen, it can be sulfur, phosphorus, silicon, etc. So this is the periodic table, gives us a glimpse of where we are looking for new chemistries, and to do those simple calculations that Faraday would have happily been doing it centuries ago. Yeah. And if you now look at but what is more important for us to look at things like radius and the charge and within the structures. Okay, that's what determines the mobility and the kinetics and is the power. It's not enough to have the theoretical energy. We need to be practically able to move these ions in these structures at that given rate that is high enough, and reverse it if possible. In fact, primary batteries are actually, they're not dying, they're still important. But I think it is this chargeable batteries that is of great interest. Yeah. For all the future solutions for energy and environment. Okay. Now, this is a simple calculation that one would do in order to optimize the energy is a product of the potential voltage and the charge capacity. And for power, you will multiply the same potential with the current. And for most applications, we have to target is to as high as possible, and you want to maximize the cycle life. Now, high voltage batteries requires high cathode electropotential and a very low, zero ideally anode potential. So the difference is as large as possible. But as soon as you have that, the electrolytes become unstable. Yeah. So therefore, you have to pay attention to that. It's not just getting a high potential, but then you have to discover new electrolytes. You have to make them stabilize. Otherwise, they will decompose. And the dangers exist as soon as these reactions take place that are parasitic. Fires, flammability issues come into play. Okay, so in order to maximize this Q value to get high energy density, which we express gravimetrically per unit weight in milliamp hour, Faraday's law is starting. And that is a simple formula for that. And any high school chemistry student knows the Faraday's law. This is what we apply. Yeah, so it's very simple. But volumetric for Q is per unit volume. That's also important, especially in electrical vehicles, etc., where you really require the volume to be small as well. So you need denser electrodes. For example, if there's a competition between magnesium and lithium, magnesium will win on that because it's denser. Yeah. So good reversibility for rechargeable cells. It's anybody who deals with thermodynamics understands looking at what a reversible reaction is feasible or not, and what kind of losses exist in the reversibility. Okay. Now, if we apply this for the Faraday's law, we need high Z atomic number and low molecular weight. So therefore, you can see that the best energy density will be for hydrogen if it is available in solid state. Yeah. Unfortunately, hydrogen is a gas. Therefore, of course, it's used as a fuel cell. It's extremely attractive. Yeah, but you have to store that somewhere. But hydrogen can also exist in a solid state. The amounts are very small, but nevertheless, it is possible to think of hydrogen still actually in a solid state in a battery. It's not been applied at the moment. It's a great area for thinking about research because it's got extremely high capacity, followed by lithium, then aluminum, magnesium in that particular order. I even put rare earths because they got huge amount of potential, the voltage. Yeah. However, they're very heavy and they're very expensive. They're very rare, but it's possible to consider that. Now, therefore, one may consider things like alloys, which are hydrogen and lithium or hydrogen and magnesium. If you nanostructure these materials, the solubility or space for hydrogen increases. Yeah. So therefore, it is a possibility that you can have, there is no reason why you have lithium battery or just hydrogen fuel cell or magnesium battery. Why not have battery which contains both these elements? Yeah. So these are future directions in which we can actually expand the idea of how batteries can operate. Yeah. So such that both elements participate in discharge reactions or charging reactions. Well, it does not have to be hydrogen. It could be lithium and aluminum and sodium and aluminum. Of course, then the research requirement is in a mixed discharging system with these components, what may determine the electropotentials. Yeah. And the anode components acting as hosts are not discharged. Yeah. That's okay. So when I said we have graphite as an anode, it is actually a passive partner. Okay. Well, it's electrochemically passive. Yeah. But it's not passive it's very safe for safety, and mechanically it's not passive. So therefore, it's going to reduce the amount of energy available for us. So we have divided the concept of simple anode factor calculation. So very simple table will tell us it's a multiplier or a divisor. For example, lithium-ion battery using a carbon anode, the Fa is 0.1 compared with pure lithium is 1. So that's what I was saying, it's less than 10% that you get the energy. You're not using the lithium fully, really, for safety purpose. And so then, but of course, if you use silicon, it's much higher. It's a several-fold factor, but it's unstable. So therefore, the future is looking at combination of carbon and silicon, for example. So therefore, you take advantage of carbon for its stability and the graphite, its safety features, but silicon for its energy. Yeah. So this combination might work. Yeah. So I think just giving you a flavor of other possibilities before I get into lithium sulfur. And this is an area that shows how not only you can turn a graphite this is a crucible here, into graphite into various forms of carbon, which can store more energy than the 372 milliamp hour per gram in graphite. Because once you have a nanostructured form of graphite, carbon, essentially, there's a lot more spaces available for intercalating lithium. It's not only within the C planes that we're talking about in graphite, there are loads of other surface features where actually the voltage of it is lower than that of graphite. So you have more the increase in voltage and also increase in capacity simultaneously. So therefore, the product of the two is energy density. So it's the intercalation of hydrogen increases. And this procedure is actually using electrochemically, actually exfoliate the graphite. So the advantage of doing that, not only you produce a graphene structure, for example, or nanocarbon structure, you can also embed silicon into the same carbon structure, like by using silicon oxide. It deoxidizes, and you get combination of carbon and silicon. Now, silicon is mechanically otherwise unstable, but when it's encapsulated within these graphene planes, it becomes very stable. It is absolutely able to mechanically take the load. Yeah? Otherwise, silicon, when it expands because lithium is reacting with it, it actually fractures during the charging and discharging cycles. Yeah? Okay, so therefore, high performance anode materials can be produced, for example, by using this approach. Yeah. Okay. Cathode, whatever you do, yeah, your question?
Just back last slide. You didn't say under graphene, the expansion of silicon is open, or is it just kept in check?
Kept in check. You cannot, it's a good question. You cannot do away with it. Yeah, once a lithium reacts with silicon, there's a huge volume change, and in the discharge in the charge, the delta V is maxed. As a result of that, it mechanically degrades, yeah, and loses contact with the conducting particles. But once it's encapsulated like this structure, it is mechanically as if it's breathing. Yeah. Okay.
Thank you.
Yeah. Okay. When a cathode is considered, we need a reactive host. So therefore, whatever we do, the cathode weight factor is always going to be 1. Say take cobalt oxide, the cathode factor is 0.04. Yeah, because we need a very stable host. It is the molecular weight of the host material that determines the energy density. That's why when you use cobalt and nickel and manganese and iron, we actually lose control over the molecular weight. It's very, very high. Yeah. Oxygen gas is a nearly zero weight option. Not really, because the supporting electrocatalysts, the binders, the conducting materials will add weight. Despite that, it is theoretically possible with some more research, maybe more than a decade, to achieve FC of 0. That's very attractive. So now we have a lithium and oxygen, or lithium and air batteries. They're almost like a semi-fuel cell. Yeah. So I think we can see that in maybe 20 years' time, we might have those as an option. Sulfur is a good candidate due to its low molecular weight and a very high value of Z2. So FC is 0.2. Can be achieved. Now you can imagine compared to lithium cobalt oxide, which is 0.04, how good sulfur is. Yeah. Of course, there's a whole area of research in organic perovskites, which are very light, in which both hydrogen, lithium, and other elements can be inserted. So it's a difficult area at the moment, but that's a very, very interesting area to look at these kind of cathodes. What we require a very low thermodynamic activity of the electroactive species to obtain a high cathode potential. Lithium in lithium cobalt oxide is extremely low activity, for example. The electrolyte stability becomes extremely important in those situations, as I mentioned before. Yeah. Okay. There are other areas of interesting research that it's just absolutely at a very basic stage. I want to talk about that. Yeah. Few words about electrolytes. Okay. We can have aqueous salts, salt dissolved in water, organic solvents with salts dissolved and solvated in them, solid electrolytes. I mean, this is a new upcoming option, and ionic liquids is also an area of research. Yeah. So I think what we require here, these must be of low weight and high ionic conductivity and low electronic conductivity, and extremely high transport number and very stable. And also the safety features must be self-quenching under heat or shut the battery if it gets hot. Yeah. Thin solids or gels or immobilized liquids in kind of hierarchical porous membranes, so that there is a good conductivity and all the properties are met. Okay. And of course, we need the right type of additives so that there is a stable interface that is formed at the anode and the cathode. Or it can depassivate, that can depassivate the electrodes. Yeah. Or electrochemically polish the dendrites that are formed during discharge. So there are many functions these electrolytes and the additives have to carry out within the battery. So therefore, that's an intense area of research by itself. Yeah. And of course, there are the solid electrolytes. We will begin to see that composites may actually steal the show there. Okay. Yeah.
There are ways to get rid of dendrites.
Yeah. It's a serious problem. So lithium-ion batteries, the dendrites, when they form, there are a number of approaches. One is using a solid electrolyte, for example, because solid electrolyte, if it is a true solid electrolyte and does not allow, but dendrites go through the defects, the grain boundaries, for example. So it's not been problem solved. Yeah, there are other solutions. I'll come to that towards the end of it. Yeah, there are other solutions. The dendrites, when they form, so they're diverted rather than going straight to from the anode to the cathode. Yeah, so there are structures called 3D electrodes. So therefore, of course, you're basically looking at the nucleation and the growth. You want a large amount of nucleation, but slow rate of growth. Yeah, but of course, it's very basic phase transformation. Yeah, that is what is required. Or you make sure it's not directional, because the dendrites, when they're directional, and it's a soft solid, lithium example, or sodium, they're soft solids. So they don't require to penetrate like a needle. They can, because whenever there's a power, there's a heat. So they become even softer. So they can bend and move as well. Yeah. So when anode and cathode contact each other, there is basically a possibility for fire and explosion. Yeah. Okay. Yeah. So lead acid battery invented in France in 1858, look at energy per unit volume or per unit weight. And then each of them came nickel metal hydride, which looked fantastic in 1990. It was very quickly superseded by lithium ion. And the lithium-sulfur is somewhere there. I say 2015 because there are a number of these batteries already in play in the aerospace and the defense industry. Yeah, it's semi-commercial, let's call it. Yeah, okay. And some drones use them already. Okay, yeah. And some of the others I just mentioned in their positions, because there are some advantage with some of these batteries, because the resources, you can't have just one battery, you'll have many number of batteries for different applications, because otherwise you'll have a supply chain issue. So I think there's a whole range of batteries one has to consider. For different places, cost may be very, very important in some areas. Material supply may be very important. So there are many factors there to consider. Okay. Now lithium-sulfur battery is actually exactly the same architecture. It's called lithium. It could have carbon or some other host, but pure lithium, and it got sulfur as the other electrolyte. And it's got a liquid electrolyte with organic solvent containing a lithium salt. And the architecture is exactly identical to lithium-ion batteries. One advantage of that, existing assembly lines can very quickly adapt to this one. Yeah, so if you have a lithium-ion battery assembly line, you can incorporate lithium-sulfur into it. So there is no development cost for making a new type of an assembly line. So that's very, very key for moving forward. Yeah, because all the available infrastructure could be utilized. Okay, and then you can see if sulfur, there's a sulfur particle and there's a carbon additive for conduction, and there's a polymer binder to hold them together. It's very similar to the lithium cobalt oxide and other oxide electrodes used in lithium-ion battery. Okay. Yeah, but what stands out, you can see lithium-sulfur battery is this massive energy density available. All we need to, at the moment, look for 25% of the energy, reversibly available, stable, and safe. It will be much better than lithium-ion battery. So already lithium-sulfur batteries look so promising in this direction. Yeah. But what are the problems? Let me highlight some of the problems. It's a very complex chemistry compared to lithium-ion batteries, which is an intercalation from one structure to the other structure through a liquid electrolyte, through a membrane which is flooded with liquid electrolyte. The membrane is simply nothing more than a polymer. Yeah, sometimes reinforced with oxides like silica. Sulfur is partially soluble in those liquid electrolytes. And when it reacts with lithium, it forms polysulfides in a polymeric chain, which is fully soluble in the liquid electrolyte. And then as the discharge progresses, it forms other polysulfides, which are partially soluble to insoluble. And finally, it becomes Li2S, is fully insoluble. So you start with an insoluble material and end up with an insoluble product. And that makes the whole morphology construction very, very difficult. Because by itself, an insoluble and non-conducting, they're both, this is highly insulating, lithium sulfide is highly insulating solid. The reaction will not take place on the surface. There is no pathway for electrons and ions. So you need to, in a morphology, connect this to a conducting material like carbon, for example. Yeah. Such that when the volume expansion takes place and the volume decreases as a result of the reverse reaction, it doesn't lose contact, which is invariably does. Yeah. So this morphology construction is the challenge. It is really the work the material scientists do all the time. You look at morphologies of your structures, especially in composites. Yeah, these are composite structure, and you need a binder to hold them together. Okay. And of course, we can see the capacity, a lot of capacity is available at the later stage. But our aim perhaps is to just use the capacity up to here. It will still beat the lithium-ion battery. Yeah, without any problem, at a lower cost, without need for cobalt, substitute cobalt with sulfur, for example, or nickel. Yeah, and the price of nickel is going to go really high because the demand for it is going to be so high as the pressure to decrease the amount of cobalt in the lithium-ion battery gathers pace, nickel will increase. Yeah, which is good for Canada because Canada has a lot of nickel resources. Yeah, of course. Okay, so I think this is the same figure. I've just shown you the regions in which this capacity arises, and the reactions I've written in terms of ionic reactions here. I think they don't have to spend too much time on that. Let me just give you some problems. Yeah, so therefore it's, as I mentioned, insulating. Sulfur and highly insulating. Some of the best insulators, actually, you can imagine. High solubility and diffusivity of polysulfides. Now, if something dissolves and there's a concentration gradient, it will parasitically move to the other side. Instead of staying with the cathode, it will move to the anode. Yeah, so this is the anode, this is the negative electrode, and this is the positive electrode. Yeah, I know people call anode and cathode. I do it as well. Remember, when you charging it, it reverses the anode and the cathode. Yeah, so we just remember. But everybody calls this an anode because in discharge mode, this is the anode, this is the cathode. The polysulfide that form here will diffuse. And that is, some of it will dissolve, some of it will react with lithium chemically. So that kind of energy is lost. So there's a tremendous amount of loss of energy, capacity fade that takes place. Yeah. Okay. And there's a volume expansion that takes place on this side when sulfur becomes Li2S. Yeah. And therefore, then you find that this material begin to break down as well. Yeah. So when for reversing the reaction, it becomes harder. And here, a lot of energy comes from, you're going to use pure lithium metal anode. The anode factor is going to be 1. not 0.1. Yeah. The reason why we can do that is although the dendrite will still form at very high power rate, you cannot stop that because you are forcing the growth rate because there's a electrochemical gradient is very high. But we also know because of this diffusion and the reaction between the polysulfide, it's a polishing action. If a polysulfide diffuses to the lithium side, then it starts polishing the dendrites. Okay, so therefore there is, if you at least at the low power rate, it's a very safe battery that can use pure lithium. Yeah. Okay, but however, if it doesn't form dendrite, it forms various kind of mossy lithium. It sort of leaves spaces. Yeah. So therefore, that lithium is never in contact properly with the electrolyte. And there is what is known as solid electrolyte interface. That's a key in a battery, because that electrolyte interface must be ionically conducting, but be stable and not consume so much of the electrolyte that it keeps growing. Becomes then after a while, it cannot have much power left in it because it's a huge resistance. So, and that must be stable. It's a dynamic process. It's not built once and stays like that. It dissolves, reforms. And that interface for stability, and one can, of course, there are many techniques studied, not only by microscopy, there are in situ microscopy and spectroscopy as well, but also by studying it by impedance spectroscopy, where you can really monitor the impedance of this layer, of a thin layer, whose capacitance therefore becomes very, 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 very high. Yeah, because it's very thin layer. Okay. Now the electrolyte organic solvent, yeah, I mentioned that, of course, you can change the nature of electrolyte to control the diffusion rate and the viscosity, etc. But however, that is as a result of those reactions, you have a loss. And electrolyte itself can contribute to safety by actually getting hot and vaporizing and creating various gases. And there is a separator in all of these materials, which actually tries to keep the anode and cathodes away from each other. If that separator became a solid electrolyte by itself, that will have a huge impact on this battery. Now let me give you yeah. Yeah.
Please. Don't quite get the blocking before that.
I think there is, yeah. There is a separator, yeah, separator is, yeah, in between, and let's say it's a macroporous material, and through which all the, basically it must contribute to lithium-ion conductivity through that. Yeah. But if there are polysulfides formed and they block the pores, the lithium-ion cannot move through it. Okay. Yeah, so therefore it requires, if you make it too large, for example, then the polysulfide will diffuse. If you make it too small, they'll get blocked. So there is a whole separator engineering. It becomes critical. Yeah, and these are the problems that are being slowly solved, I think. Yeah. So if this, see, I'm mentioning all these different problems because every one of them, at the moment, you'll find thousands of papers on lithium-sulfur batteries, because people are solving bit by bit, and then there is a, the conferences, the discussions, etc., to see whether we are making net progress, yeah, from the laboratory to the next stage. Right. Okay, I showed this paper because this was from a Canadian university in Waterloo. I think one thing what they did is they showed that if you use a very strict, it's like a map of carbon perfectly aligned microstructure, yet created by some kind of a template technology, and then you infiltrate that with sulfur, yeah, and this carbon structure remains intact, as if the path of sulfur going in and coming out and reforming is like entering a city whose map does not change. I came to McMaster today, I will be completely lost from a memory 20 years ago, but the map is completely changed now. Yeah. So this is retaining the map in such a way the positions are identical for the formation of the sulfur back. Yeah. And when it goes again, it leaves the structure intact. So this, okay, so there's a whole range of microstructure morphology to be considered here. Is, yeah, so this, I think this idea gave a lot of people suggestions that we have to look at this microstructure in great detail, understand what is it that require to get some kind of energy dense capacity which remains stable as you cycle. Yeah, this is, even though the number of cycles are only 20 here, but it's pretty stable, is one of the early work which suggested the possibility that maybe we should play with the morphology, understand what's causing it. I'll just show you some of the work that immediately we followed on that. We used a metal organic framework material and pyrolyzed that, converted, because it's got zinc in it, zinc also actually vaporizes, converted that into a hierarchically porous carbon. Yeah. The beauty of using metal organic framework, there are thousands of these metal organic frameworks available. Yeah. And they start with extremely high surface area already. So if you make this is the BET surface area, you can have a surface area of 1,000 to 4,000 meters square per gram. It's extremely high surface area. Yeah, like zeolite materials there. And incorporate the sulfur into them. Then you look at the sizes of the pores. You get so-called micropores, or sort of, few nanometers. Mesopores are 2 to 50, mostly 2 to 25, and macropores are the very large pores. You get 3 kinds of pores, and you have a total pore volume. So you can also calculate that by the BET surface area measurements, and the pore volume are within this region. So we did loads of these materials. I'm just giving examples of few. And we immediately saw, even though they're all morph precursors, all have different surface area, and they have a different distribution of those different pores. I mean, looking at that, then we worked out, whenever you have a high BAT and high mesopores, it can take high amount of initial sulfur. It's got a very high initial capacity. Initial capacity is given by the first cycle. Yeah, by the first cycle. Okay, of that cell. Okay. But if you have too much macropores, very large macropores, the capacity drops very quickly. And if you have a mesopore, which is high, that is the 2 to 25, then you have a high initial capacity. Micropores gives cycle stability. So this is the compromise. Yeah? Okay, so I have not quantified here, but we've been able to quantify what might be the right optimization between these 3 pores, so that you get not only high capacity as possible, but it's very important to keep it stable. It's no good having a very high initial capacity. After few cycles, the energy has gone down, capacity has gone down. So it's very critical to keep it stable, even if the high initial capacity is low. Yeah, that's more important, because there is a requirement of a minimum capacity and a large cycle stability. Because if this was going in electrical vehicles or drones or aerospace applications, you can imagine the cycle life is so important. It must sort of at least have comparable to lithium-ion batteries, which is about 1,000 to 2,000 cycles. Following the same principle, of course, nobody is going to use metal organic framework and pyrolyze it and use it as an electrode. Yeah, it's too expensive to do that. But it's possible nowadays, because we can have various structures of carbon. This is an example of carbon in the form of a forest. You get carbon nanotubes growing from a substrate, which could be simply the current collector. And you can have the gaps between these trees and the gap between 2 sets of trees. You can vary that. And using the formulation, we clearly showed whenever you have this very high density, then you had not only high capacity, you have very stable cycling as well. And of course, if you purposely keep them all apart, far apart, then immediately, even though it's still stable, the structure is still stable, but it's very low capacity. Yeah, keep asking.
I lost it. Where you had
Come back to you. I'll leave you to. Yeah, carbon nanotube. Yeah, forest. Yeah.
Please continue a little bit from there.
Yeah. Okay. Yeah. So of course, so there for that, and then we work with some people who are modeling on a regular basis to look at what is the reason for this. Yeah. So therefore, how interaction of the various sulfides and polysulfides relate to the wall-to-wall distances within the carbon nanotube. Yeah. So therefore, from the energy changes, we know what might be the right combination. And you can do the same with graphene structure. Yeah, this is again, you take a template like nickel, porous nickel, and you grow the graphenes in and then dissolve the nickel away, for example, or copper away. And then you get this structure. These are the graphene structures. And this also, you can see now, the capacity is very, very high. And remember, there's a lot of pores. At this magnification, you can't see. Most of those micropores or mesopores are within the structure. Maybe the next graph will show you that. Yeah, you can see that. Yeah, this is the few layer graphene. Yeah, there's a large amount of capacity available at all those surfaces. Yeah. And although this is at the lower magnification, this is the higher magnification. Yeah, and similarly for the carbon nanostructure, we can look at very high magnifications as to where those capacity resides, where the sulfur interacts with the structure and actually produces the capacity. Right. Okay, so therefore, but we haven't solved one problem to understand how we absolutely minimize the shuttling. Because one problem that lithium-sulfur battery has, lithium-ion battery does not suffer from, is when the capacity of a lithium-ion battery decreases, which it does with cycling, we are aware of it. There's warning, it slowly declines. But lithium-sulfur battery does not do that. Because the shuttling is one of those catastrophic processes, what can happen is battery might be working perfectly well today, but suddenly it goes. Without it, there is performance declining slowly. Yeah. Or the charging times take longer, etc. No, it just declines. Yeah, and that will not be acceptable for mobility, electrical vehicles. That could be extremely dangerous. So I think therefore, we need another method by which we absolutely make sure that this shuttling phenomena process is stopped. Yeah. So there is of course the trade-off between the capacity and the cycle stability. So cycle stability must be predictable. It must guarantee for most of the batteries, certain amount like 2000 might be the aim, for example. And how can we guarantee it? Yeah. So therefore, it requires new ideas. Yeah. One idea is because we know the shuttling takes place because there's nothing stopping the diffusion. Yeah. As I said, that to some extent, we don't want to stop the shuttling because that is what actually is electropolishing the dendrites. So we want the shuttling to take place at a minimum amount, maybe a few percent, but not freely under concentration gradient and electrochemical concentration gradients. It just shuttles away. So one idea for that is that you have interlayers. The interlayers have a capacity to slow down the shuttling because when it doesn't shuttle away, the electrochemical reaction takes place. If it shuttles away, there's no opportunity for electrochemical reaction. So therefore, there is a rate at which reactions take place and the rate at which it shuttles away. So we need to maximize one. Of course, we want for power, we want the electrochemical reaction to take place very fast. Yeah. So of course that is, but there's a limit. It reaches its own limit after a certain level. Then we want to make sure that the shuttling rate is controlled. Yeah. So but now if you're doing materials chemistry day to day, you can think about various materials that will actually act as an inhibitor of. Yeah. Now this is an example. There was a carbon interlayer. This was accidentally found that a carbon that was put as a material actually led to this advantage that the capacity was stable and was very, very predictable. And the carbon is not the best material for that, of course, is that some materials which have a good reaction with sulfur, such as zinc, and has got a good microstructure like zinc oxide. So you can see that these are nanowires grown on a nickel foam. This is very, very heavy, so you have to make it very thin. And when the polysulfides contact it, yeah, they slow down. They actually act as like a traffic signal. They slow down considerably. They therefore allow the electrochemical reaction to take place on the cathode. So therefore, they don't shuttle away. They hold them back. So you have to keep it as close to the cathode as possible. Yeah. So you can see the microstructure of this is such that it's almost like the intestine behavior. It just holds on to those materials. And of course, we can have a brush-like structure as well. Yeah. And it is possible because the whole nanostructure engineering is such that we can produce all of this through hydrothermal processes and other processes that, yeah, or you can look at the high magnification. This is, yeah, you can see how they look like a brush. It's perfect for the liquids to go through it, but the polysulfide to be held back. Yeah. And this is another structure is actually, is the backbone is all made of carbon and the titanium oxide, because we know zinc, titanium, etc. actually have a very high affinity for sulfur. Yeah, they want to form oxysulfides, etc. Yeah. And such a material can be very easily made as well. It is done by electrospinning, for example. You combine polymer with the titanium oxide and pyrolyze it, and you end up with this structure. And this structure you can see is highly flexible as well. So therefore, in the flow system, it's not a rigid structure, so it's not going to break. I think the few points I'll just make about the dendrites. As you said, it's very easy to understand how the dendrites form. We know how it forms in solidification. There are gradients which lead to this instability. Yeah. And in this case, we have the gradients related to the electrochemical potential and the chemical potential. And under the field, you will find that any of this lithium that is ahead is going to move more fast, because the gradient is decreased. And as a result of that, we have to think about various ways by which we do not allow that to take place. One approach that we see in the nature is having some kind of interlayer, like a lithiated molysulfide coating really seem to quite work very well. And that instead of having one kind of a big dendrites forming, there are many dendrites forming, and they then never quite reach the cathode. And one can also electrochemically measure this by looking at this is a very stable, the dendrites are not forming. When you have this departure, there's a huge over potential. That means the dendrites are forming.
Really on the structure where the dendrites don't quite reach the top.
I think what happened, what happened? Because there are a lot more surfaces over which dendrites form. The electrolyte is filled into the 3D structure. And therefore the dendrites form and they grow in different directions. Yeah, the gradients are all not in, say, let's say, in one axis. Yeah, it's in 3D, 3 axis. So so therefore the growth of the dendrites. There's a company now actually routinely are able to apply this and produce a 3D structure. The difficulty of making the 3D structure is expensive at the moment. But whenever they make that, there's no problem. Of course, what they do is they use a light scaffold onto which they coat the lithium. And the lithium is pure lithium coated onto a conducting light scaffold. Yeah, and therefore that lithium, is distributed in 3D rather than a planar lithium foil. And therefore the dendrites are formed all over the structure. Yeah. Yeah, and I think you'll see increasingly, you will see that solid electrolytes become very, very important in the future. We'll replace the separator and liquid electrolyte with solid electrolyte. But that's an area, but all the companies are claiming to be doing a lot of work on it, because that I think will be the future of safe batteries. Because of course, at the moment, if you make a solid electrolyte of pure ceramics, it doesn't fit in with the assembly line, because ceramics have to be sintered at high temperature. But assembly line does not have that facility at the moment. So that will make it very complex. But if you use the solid electrolyte on as a substrate, you can't make it very thin. Then it's very resistive. It's not conductive enough. Yeah. So you can imagine there are many, many such problems. Yeah. Okay. If you have a solid electrolyte, which is made out of a ceramic, you have to sinter it. Yeah, so that's high temperature. It's the kind of lithium ionic materials sinter at about 1100 degrees centigrade. So you can't incorporate that into the current assembly line. Yeah, but if you make that as your substrate, yeah, then you have to make it thick. You can't make 10 microns of it. There is no method, but it can't be freestanding. Yeah. So if you have 100 microns, the resistance is so high, it will not conduct until it reaches temperature 150 degrees centigrade. The batteries have to work at 150 degrees centigrade. It's possible. That's not impossible. But yeah, that may be another solution. Or you can go and use what is known as combining these ceramics with polymer and make composites. So therefore, both ceramics containing the salts of lithium salt and with the ceramic. So that is the direction in which it's moving at the moment. Yeah. Okay. But the stability is also important. If we increase the potential between the anode and the cathode to as high as possible to get the maximum energy, then the electrolyte, especially some polymers, may decompose. Yeah. So the problem is not solved, but I think all kind of dopings and all kind of solvating and amorphizing the polymer to make sure it doesn't decompose is important. Yeah. Okay, I think the safety is that's key. As I say that if any of these batteries we make, no matter what, they are always prone to catching fire, especially because of abuse. Yeah, especially because of charging at a fast rate, or just the appliances that you use to charge them are faulty. During charging, they are under great danger. Or they may be charging during driving. That's extremely dangerous because you may have a feature alternator to charge them. And under all those conditions, the danger exists. So we need a diagnostic method as well. So I think constantly we are developing various sensors that will also even complement, not supersede, the battery management system that already exists. But that has not helped minimize the number of accidents. So we need another approach, and we're looking at all the gases that come out overcharging from the batteries, and this is applying it to lithium-ion batteries, and we know all the different gases come depending on the situation. But thermal runaway is too late, so we need to be able to catch somewhere here. Yeah, when it's getting hot, temperature measurement and gas measurement. And for this, we need really, really small sensors to be able to incorporate into the cell system as well. Yeah, so this is some of the work other people have done, looking at what kind of gases come out. Yeah, so you can see hydrogen is a very prominent gas early on. It already shows if hydrogen comes out, you know that some danger is building up. Yeah, so the potential control is possible. Or perhaps one of these ethylene carbonate or diethyl carbonate vapors. That may be a second stage. Yeah, so we are building sensors based on semiconductor chip and monitoring our own batteries when we make them and see how these gases come out. And you can abuse in a laboratory within a closed system. Yeah.
These stages happen independently, or
I think that stage perhaps is early on, just is involve the moisture. But after this, they can all happen very quickly. And a catastrophic situation, there is no gap. Yeah. So I think this is sensor. I think the university has licensed to a company who are making this systems and package for gas analysis, and we have been trying it with some companies like Bosch, etc., who are involved in the battery management system to see whether they are able to pick up these gases. Yeah. Okay, that is an example of the company which makes these sensors. Okay, I think I'm going to stop there, and thank you very much for your attention. And there are any questions, I'm very happy to answer.
Thank you very much for this great overview of all the potential improvements that could come in the lithium-ion battery field.
Yeah.
Wasn't why don't we consider fluoride ion as the conductive tissue? That's what I
Yeah, so fluoride ion as a conductor, it's a lithium and fluorine. Yeah, I mean, yeah, I think it's a very good point. I mean, from periodic table, that has the maximum possible energy. There is no doubt. Yeah, but electrolyte stability may be important. That's why the ionic liquids potentially can be more stable. Yeah, so that's absolutely right. But of course, there are shortcuts, aren't there, to lithium fluorine batteries. The shortcut is use carbon monofluoride. That battery is a primary cell exists, it can't be charged back. Yeah, so therefore we already know the lithium fluorine is a yeah. But you're thinking of fluoride ion as a conductor rather than lithium as a conductor. Okay, I see what you mean. Yeah, I don't think any work is done on that at the moment. Everybody is looking at lithium ion as a conductor. Yeah.
Because lithium supply.
Yeah, right. Okay, so yeah, sure. So you're looking at fluorine ion as the conductor, and what is the anode? We have to, yeah. I think we have to go back to the periodic table to look at what's possible. Absolutely, I think you're right. Fluorine ion can have a good conductivity at low temperature. Absolutely right. Yeah.
So it seems that sulfur solubility in the electrolyte is the big problem that you're trying to overcome.
Yeah.
Anybody thought about trying to use a cathode like the lithium cobalt, right? Which is except for the cobalt oxide.
Yeah.
Cobalt sulfide. They seem to
In fact, yeah. See, the very first lithium batteries, for which the Nobel Prize was given, was based on sulfides, titanium sulfide. Yeah, and the lithium titanium sulfide. So that is the principle. So therefore, of course, as soon as we have a heavy metal, titanium is lighter, of course, but as soon as you have that, then the energy density goes down because we are but that is solution, because there is some advantage in going back to the sulfides, because there are good sulfide electrolytes which have a very good conductivity, even though they are ceramic, but they're soft solids. They sink under pressure at about 50 degrees. Yeah, so they can be doped. Yeah, this is the kind of area Jacob is expert on, how to increase ionic conductivity by doping of materials. I mean, that's an area, I think there are some people looking at it, but not many, I think. But it's a good point. Yeah. So
you're saying basically that it's not competitive to have a sulfide compound.
At the moment, it seems like that, because there are at the moment, but there are some people are actually asking that question. Why don't we have a solid electrolyte, which is a sulfide as well, which is ionically conducting, and a metal sulfide, which is precisely the kind of work which is done before good enough came with the cobalt oxide. In California, the first batteries were titanium sulfide, which won the Nobel Prize because that showed the way forward. Yeah. So yeah, but it might it may come back because we have a solid electrolyte, and we have a pure lithium on one side, and it's chargeable, and it's safer perhaps. Yeah. Because I think the slightly lower energy density, as long as it is utilizing all its capacity. See, the lithium-ion battery, you never discharge for electrical vehicles below 80%. So you're only using the 100 to 80%. Yeah. So that's why they have a second life. So they sell it off to other things. Yeah. So if something can use more, then it will actually have more capacity, more energy at least, because the capacity, this product of voltage and capacity together. Yeah. So I think that's where sodium-ion battery is suddenly getting very interesting, because it uses the full capacity. It's safe. The end of the battery life, the current electrical vehicle battery, is dangerous to even to transfer it, because it's got so much energy left in it. Yeah. But a sodium-ion battery can be fully discharged before sending it out, as an example. Yeah. So I think, and they're also looking at other, like not the cobalt, but the lithium iron phosphate. Yeah, it was discarded. I think China actually did a lot of lithium iron phosphate initially, because they had lower energy with them. But they also they're not discharging it fully, because they thought all these batteries, you shouldn't discharge it fully, never have life again. But they found out it can discharge very close to 100%. So lithium iron phosphate suddenly become the popular. Yeah, so there's a US company which actually Reliance bought it from India because this is low cost materials. They don't need cobalt and nickel. So yeah, so I think so it's an example of how the old knowledge comes back because you understand it better here. So I think, yeah, so I wouldn't rule out any of those things. I think we have to that's why I keep periodic table in front of our students, say, go back every time to see what's possible. Yeah.
Interesting.
There are two statements that you made, that the technology seems to decide requires large nucleation rate, but low growth rate. Right?
Yeah, relative ratio between the two. Yeah, yeah.
That's one.
Yeah, yeah.
Other one you mentioned also, I think it was coming up somewhere. I was fascinated by your dendrites.
Yeah.
And we have been involved in dendrites with that.
I know, exactly. Yeah.
So one of the major things that came out of the last series of work, classical work was Williams and Sakata's work on interface instability, like the effect of capillarity on interface instability.
Yes, yes.
So even though these are all maybe very unrelated field to what you are doing and not very close to this field. So in fact, this I just wondered how those classical papers fit in with what some of the observations that you are trying to engineer, as I understand. Essentially being a nanoscale engineering.
It's a very good question. I think we have to bring all the metallurgists into this subject. Of course, the constitutional supercooling is the main cause of it. There can be potentially thermal supercooling as well, but that's rare, but constitutional. But here, if you think the same approach supercooling, it is the gradient, is electrochemical gradient and the chemical gradient. Yeah, they're both operating, and therefore what it is, they're creating instability because the gradient is reduced. Yeah, so it's exactly the same principle, but a different different physical driving force, but the same idea. So I think, yeah, so I think there is a lot of people who work in this area are not fully aware of that knowledge as to what this gradients, how therefore is going to drive it. If you know what is driving it, then how you can minimize it. So, but this 3D idea is actually come precisely from some metallurgists. Yeah, they can see that dendrites will form, you can't stop it. But if you nucleate in many locations, if you have a planar, you have lost that. Yeah, you cannot, because as soon as you nucleate in one place, you can't nucleate next to it. There's be a gap. Yeah. So because the gradients are, difference. Yeah. So therefore, if you have a 3D space, the nucleation possibility. I mean, we haven't fully understood it myself how that happens, but I've seen the results of some of them. It's amazingly surprising that the dendrites form with all those structures inside. Yeah. So
most fascinating is the CCM, you are able to go back and absolutely nanoscale.
Yeah.
You wanted to say to some of the talk from these guys who are doing doing, but basically it seems to me some of the core concepts which evolved way back are not being threaded in properly.
They're not. That's exactly. Yeah. I think. Yeah. I forgot to mention my friend Luigi's name. Of course, we know Chera from Cambridge. He's an expert in all kinds of things, which is so relevant for the battery. Yeah. I know. Yeah.
I wonder if we have any questions online. No, we're all good.
Yeah. One more question. Yeah.
One of the main points that going from the sulfide, the oxide-based cathode material, is the energy gap between lithium and sulfide and lithium and oxygen, which gives the potential to have higher voltage at the end, so it can give us much more energy and power.
Yeah.
But here, from your graphs, you only have a gap 1 volt or something like that. 1.5. Or is there any?
Very good question. Very good question. Absolutely right. The lithium cobalt oxide has 4.2. Yeah. And the manganese oxide spinel. This cobalt oxide is a perovskite. Spinels even higher, 4.5, 4.6. people are actually going after them. The manganese is low cost material everywhere available. So you can see there's a huge, at the moment, what happens, manganese is not a very simple behavior. It's got a number of oxidation states. So therefore, the stability of the structure is not guaranteed. But that's one area. Absolutely, I agree with you. Lithium sulfur battery has only 2 volts. Similar to the lead acid battery. But therefore the voltage is low, but the capacity is large. The product is very large. The energy is the product of charge and voltage. But lithium sulfur battery, while the voltage is low, but so therefore if you need a certain thing to operate at 4V, you will need 2 of those cells. There is no doubt. But so therefore it may occupy more space from that point of view. But you can have a bipolar system, especially when you have a solid electrolyte. You couldn't do it with a liquid electrolyte. So therefore the lithium sulfur battery, because you're using pure lithium, it is probably the one development that will lead to solid electrolyte faster, because it requires it. You're using pure lithium. It's like a bomb, really, whenever you use a pure lithium. That's why people are afraid of it as well. Even in the lab, when you work lithium sulfur battery, small ones in the glove box, you take it out, or even you enclose everything. You think you're safe, it catches fire. So it's true. I think the safety is very important, but it's not impossible to solve. I think that's the point. But it's a fair point. But so the bipolar is required to maximize the space. So I think.
Thanks again.
Okay, thank you. Thank you.